Hi, everyone. I'm Oren. Thank you for being here. So, I'm here to talk a little bit about using machine learning models or building machine learning models using log file data. With all the changes happening, cookies are becoming less available for us, and that disrupts targeting, measurement, attribution, etc. There are solutions. There are many solutions. One of them is making a lot more from the log files, and there's a lot that we can do with log files, and I'll talk a little bit about some of those ideas. So I've been in ad tech for many years, but Data Heroes is actually not an ad tech company. We're a technology company that developed a new type of data structure that's based on a technology called Corset, which I'll explain about soon, that basically allows you to train models significantly faster, significantly less compute on massive data sets. So it lends itself to log files or other types of data sets that are massive and change frequently. So let's talk a little bit about log files. Log files contain a lot of signal that we can use. Depending on DSP or SSP log file, and depending on who it is, there's tens, sometimes hundreds of different fields in the log files. What we have seen from some of our clients, there are some fields that have a very strong predictive power. This includes time of day, geo, site, supply vendor, and device. So there's a lot that you can do with those fields, especially for lower funnel goals. What we've seen or what our clients have shared with us is that the third-party cookies add very little value for lower funnel goals if you are using those fields in your log files. You're using them, you're building grading, boosting, or random forest models. You can get F1 scores that are very significant, 0.85 or even higher, just based on those five variables. So some key considerations here. The good news is that the log file data is very big. There's a lot of data that you can use there. That's also the bad news because it makes it a lot more complicated to use. There is also a real-time environment that you have to live in for inference, which requires sub-millisecond decisions, which presents its own set of unique challenges. You need models that are very lean and fast. So the key considerations are, first of all, is selecting the right sample from the log file, both for training and for validation, and we'll talk a little bit more about selecting that right sample. Selecting the right algorithm to optimize for the goal, and also to make sure that that algorithm doesn't degrade too quickly, because some of the algorithms may perform better, but degrade very quickly because of the drift. Selecting the right features or variables that have the most signal. There's different ways to do that. Those that I showed before typically will have a lot of signal. Retraining frequently to avoid degradation. We'll talk about soon about data drift, but depending on the type of data you're dealing with and the type of client, you may need to retrain multiple times a day or daily, or sometimes it doesn't need to be that frequent. And the challenge is, of course, we have to do all this at low cost with thousands of campaigns with a lot of different requirements that we have to deal with. So let's talk about retraining frequency a bit. This is actually public data from Grubhub, from their app that they shared. There's a whole paper that they wrote on that. But if you open the Grubhub app restaurant recommendations, what they found is that if they retrained that algorithm weekly, they were able to improve the purchase through rate by just 2.5% relative to their baseline, which is no retraining. However, if they trained it daily, they were able to improve the purchase-through rate by over 20%. So in this case, daily retraining made a huge difference versus weekly retraining, which didn't really move the needle for them significantly. So the key considerations here for what's the right retraining frequency, first of all, it's the number of goals collected per day. The goal could be, for example, conversions. If you have 30 or 40 conversions a day, then daily retraining is probably not going to add a lot of value because you're not collecting a lot of new information. But if you have thousands of conversions every day, the daily training is probably going to improve the model significantly. So that's one key consideration. The other one is the drift or the model degradation speed. And we can see that depending on the algorithm that you choose, the model may degrade faster. And this is an example. This is from another paper. This is 4 different algorithms trained on the same data set with the same features, a linear regression, a random forest, an XGBoost, and a neural network. And you could see the speed in which they degraded. They all started degrading fairly quickly, but you could see that XGBoost actually degraded faster than everything else. So you have to think about which algorithm you're using and what is the speed in which it degrades. So what are the best practices for maximizing the model performance? The first is to make sure that you select the proper representative sample for your training data set, identify the most impactful features in the data set, experimenting with different features, different algorithms, and different date ranges, last 14 days, last 7 days, last 30 days, etc., to find your best performing model and retraining the model frequently. So this is very difficult to achieve when you have a lot of campaigns and you have to do this in a cost-efficient manner. There's different ways to deal with this. One of the solutions is using a technology called core sets, which I mentioned earlier, and I'll talk about more now. So basically what core sets are a way to sample your data without losing information. It's actually a weighted sample of your data set. And what's unique about the core set that it maintains both the statistical properties and the outliers that exist in the data set. The way it's done is it identifies the outliers. It basically calculates a value for each instance in the data set. Instances, these values are called sensitivity. The instances that are outliers will have high sensitivity. Instances that are normal distribution would have low sensitivity. And then based on that, it builds a much smaller subset that takes all the outliers and takes a small sample of the normal distribution and gives it a higher weight to represent its repetition in the full data set. So that's how a core set is created. And if you look at this example, these graphs, what we're seeing in the middle here is we actually took the public Criteo data set. Thank you for sharing that. We took 2 million instances of the Criteo data set, and we just chose 2 features and did a scatter plot. That's what you're seeing in the middle, and what I highlighted with that red rectangle are just some of the outliers. And then we created a core set from that data set, which is what you could see on the left, of just 50,000 samples, so 2.5% of the data. And what's important to see is that all these outliers that you see in the full data set are also retained in the core set. And again, I highlighted that red rectangle as an example, but if you spend more time looking at the outliers, you'll see them all replicated in the core set. The other thing to notice, if you look at 0, 0, you could see on the core set what looks like a big circle. And that big circle is because it's a weighted subset. So the original data set has a lot that had the value of 0, 0. The core set has just one instance with a higher weight, and that's why you're seeing that bigger circle at 0, 0 on the core set. And just for comparison, we're showing the random sample on the right, and you can see the random sample of the same size has lost the majority of the outliers. So using that core set for training, for hyperparameter tuning, gives you the same or almost the same results as if you've used the full data set. So what Data Heroes actually does is we've created a framework and a data structure that allows everyone to build and manage and use these core sets very easily. The way it actually works, it's a little more sophisticated than what I just explained about a core set. Rather than creating a core set of all your data, what we do is we create a core set tree. And what that means is if you look at the circles on the bottom, those are let's say that's your data instances, x1 through x21. Rather than creating one core set for everything, we partition it into chunks. In this case, we partitioned into 4 chunks, x1 through x6, and then x7 through x12, and so on. And we built a core set for each one. So C1 is our core set for the data from x1 through x6, and so on. And then what we did is we took every pair of core sets and we built a new core set from them. So we took C1 and C2 and built C3, and C3 represents your data from x1 through x12, and so on until we got to the root of our tree, and this is our core set tree. Now, what is the advantage of the structure? The first one is scalability. It doesn't matter how big your data set is. We can partition this. We can distribute this job. You could do it on Spark, and we can build a core set of any size of data set. The other advantage is that you can build it based on the business logic. So let's say, and probably most of your data is time series data, like campaign data. So we can actually build this based on time. C1 may represent week 1 of the data of the campaign, and C2 might represent week 2, and so on and so forth. So then if you need to train on particular date range of the campaign, that makes it very easy to do. So that's the second advantage of the structure. And the third, and probably most important for when you're in production, is that when you collect new data, you don't have to rebuild, you don't have to retrain on everything. You can actually very easily just add the new data that came in to the existing core set. You add it under an existing node in the core set. That triggers an update of the core set, the node on the path to the root. This update is very fast. It literally takes seconds. And within seconds, you have a new core set that's updated and you can train on. So this allows you to retrain very frequently without incurring lots of compute. And to put this into perspective, what we did here is we took a data set, a logistic regression model with 10 features. We trained, the red line shows us we trained originally on 2 million instances. It took us 335 seconds to train. And then we added another 4 million instances, another 4, and finally when we got to 14 million, it took us 1,850 seconds to train, so about half an hour. And of course, the more we add, the longer the training time. And then in comparison, we did the same by using a core set tree, and that's the blue line that you're seeing. And what we did initially is we took the first 2 million instances and built the core set tree. Building that core set tree just took 8 seconds, so compared to the 335 seconds it took to train on those 2 million. And then training on a core set in that tree took us just 18 seconds. And then what we did is to simulate a situation in which we're updating, retraining frequently. We added 200,000 instances and retrained again, and another 200,000 and retrained again. And what you could see here is that the time remains pretty much the same. So even as we get, it takes us 4 seconds to add 200,000 instances every time, and about 18 seconds to train. And even as we get to 14 million instances, we're still at about an average of 28 seconds to add the 200,000 instances and retrain. And of course, the more data we add here, the bigger the gap that you're going to see between these two lines. So this is what makes this structure basically very effective for retraining. That's it. Happy to take questions. Special thank you to a few of our advisors and clients that have helped with some insights and data, for Anna from OpenX, Tylene from Chalice AI, and Michael from InMarket. And I'm happy to take questions.
As you build new core sets, do you expire the oldest ones out of the set, or do you keep them in for retraining?
Basically, what you do is you add to an existing core set. So what you could do is you could start trimming the end of the core set at some point. So the old data, if you say, hey, it's not relevant anymore, you could start getting rid of the older data. Yeah, that's a good question. I didn't mention this. So our technology is available as a library. So basically, through the API of the library, you can assign different weights to more recent data. Yeah, so typically what is the core set gives, I'd say in theory, it gives results close to the full data set, but not the full data set. What we've seen in practice is that many times it actually surpasses the results of the full data set, and that already has to do with the way the optimizers are built. Optimizers are actually better at dealing with smaller data sets than larger data sets. So we find that in practice many times, especially if you're trying to train on Spark or on Databricks, you see a lot of times that training on the core set will give you better results than training on a full data set. Core sets also can be customized based on your goal. So if you're optimizing to precision or recall or F1, you can optimize the core set to a specific metric. Yeah, it's a good question. It could be done both ways, depending on what your use case is. So if your use case is you've already collected the data, then you would take the data in a batch operation and create a core set. Some of our customers are actually using it for data collection. They have lots of data, and they don't want to retain all the data. So they're using it in a streaming manner to decide which of the data to collect. So it becomes part of their ad server during inference that they call the streaming core set, and decide we keep this and we don't keep that. No, so typically in the example I just showed, the model training time was 335 seconds and the build time of the core set was 8 seconds for the same size. So typically it's a lot faster. It does depend on the amount of features though, so the more features you have, the longer the build time is. If you're getting to tens of thousands of features, then the build time could be similar to train time. But if you have tens or hundreds of features, then it could be an order of magnitude or even 2 orders of magnitude faster. You could use it for hyperparameter tuning, right? So you build it once, and then if you want to try 20 different hyperparameter combinations, you could do that on the core set without having to rebuild it. So that's one advantage of it. And the other, of course, is the ability to add more data, again, without rebuilding it from scratch. All right, I think we're done. Thank you, everyone.